Hello everyone, welcome back. I'm your friend in XO. Today we are going to continue to learn the Algebra 1, or today's mission is all about
Quadratics, multiplying and factoring.
Quadratics, multiplying and factoring. Oh, sorry. Let me say first we got this item called
Polynomials.
Polynomials. All right, let's get into it.
Let's explore the notion of a polynomial. So this seems like a very complicated word, but if you break it down, it'll start to make sense, especially when we start to see examples of polynomials. So the first part of this word, let me underline it. We have poly. This comes from Greek for many, and you see poly a lot in the English language, referring to the notion of many of something. So in this case, it's many nomials. And nomial comes from the Latin nomen for name. So you could view this as many names, but in a mathematical context, it's really referring to many terms. And we're going to talk in a little bit about what a term really is. But to get a tangible sense of what are polynomials and what are not polynomials, let me give you some examples, and then we could write some maybe more formal rules for them. So an example of a polynomial could be 10x to the 7th power minus 9x squared plus 15x to the 3rd plus 9. This is a polynomial. Another example of a polynomial, 9a squared minus 5. Even if I just have one number, even if I were to just write the number 6, that can officially be considered a polynomial. If I were to write 7x squared minus 3, let me do it in another variable, 7y squared minus 3y plus pi, that too would be a polynomial. So if these are examples of polynomials, what are examples of things that are not polynomials? Well, if I were to replace the 7th power right over here with the negative 7th power, so if I were to write 10x to the negative 7th power minus 9x squared plus 15x to the 3rd power plus 9, this would not be a polynomial. So I think you might be sensing a rule here for what makes something a polynomial, that you have to have non-negative powers of your variable in each of the terms. And I just use that word term, so let me explain it, because it'll help me explain what a polynomial is. A polynomial is something that is made up of a sum of terms. And so, for example, in this first polynomial, the first term is 10x to the 7th. The second term is negative 9x squared. The next term is 15x to the 3rd. And then the last term, maybe you could say the fourth term, is 9. And you can see something, let me underline these. So these are all terms. This is a 4-term polynomial right over here. And you can say, hey, wait, this thing you wrote in red, this also has 4 terms. But we have to put a few more rules for it to officially be a polynomial, especially a polynomial in one variable. Each of those terms are going to be made up of a coefficient. This is the thing that multiplies the variable to some power. So in this first term, the coefficient is 10. And let me write this word down, coefficient. It's another fancy word, but it's just a thing that's multiplied, in this case, times the variable, which is x to the 7th power. So the first coefficient is 10. The next coefficient, and actually let me be careful here, because the second coefficient here is negative 9. So we are looking at coefficients. The third coefficient here is 15. And you can view this fourth term, or this fourth number, as the coefficient, because this could be rewritten as, instead of just writing it as 9, you could write it as 9x to the 0 power. And then it looks a little bit clearer like a coefficient. So in general, a polynomial is the sum of a finite number of terms, where each term has a coefficient, which I could represent with the letter a, being multiplied by a variable, being raised to a non-negative integer power. So this right over here is a coefficient. It can be, if we're dealing, well, I don't want to get too technical. It could be a positive, negative number. It could be any real number. We have our variable, and then the exponent here has to be non-negative integer. So here, the reason why what I wrote in red is not a polynomial is because here I have an exponent that is a negative integer. Let's give some other examples of things that are not polynomials. So if I were to change the second one to, instead of 9a squared, if I wrote it as 9a to the 1/2 power minus 5, this is not a polynomial because this exponent right over here, it is no longer an integer. It's 1/2. And this is the same thing as 9 times the square root of a minus 5. This also would not be a polynomial. Or if I were to write 9a to the a power minus 5, also not a polynomial because here the exponent is a variable. It's not a non-negative integer. So all of these are examples of polynomials. So there's a few more pieces of terminology that are valuable to know. Polynomial is a general term for one of these expressions that has multiple terms, a finite number, so not an infinite number, and each of the terms has this form. But there's more specific terms for when you have only one term, or two terms, or three terms. So when you have one term, it's called a monomial. So this is a monomial. This is an example of a monomial, which we could write as 6x to the 0. But you could also, another example of a monomial might be 10z to the 15th power. That's also a monomial. Your coefficient could be pi. It could be pi. So we could write pi times b to the 5th power. Any of these would be monomials. So what's a binomial? Well, binomial is where you have two terms. Monomial, mono for one term. Binomial is you have two terms. So this right over here is a binomial. Binomial. You have two terms. And all of these are polynomials, but these are subclassifications. So it's binomial, you have 1, 2 terms. Another example of a binomial would be 3y to the 3rd plus 5y. Once again, you have two terms that have this form right over here. Now you'll also hear the term trinomial. Well, trinomial is when you have three terms. Trinomial. And this right over here is an example. This is the first term, this is the second term, and this is the third term. Now, the next word that you will hear often in context with polynomials is the notion of the degree of a polynomial. And you might hear people say, what is the degree of a polynomial? Or what is the degree of a given term of a polynomial? So let's start with the degree of a given term. So let's go to this polynomial over here. We have this first term, 10x to the 7th. The degree is the power that we're raising the variable to. So this is a 7th degree term. The second term is a 2nd degree term. The third term is a 3rd degree term. And you could view this constant term, which is really just 9, you could view that as, sometimes people will say the constant term, sometimes people will say the 0th degree term. Now, if people are talking about the degree of the entire polynomial, they're going to say, well, what is the degree of the highest term? Or what is the term with the highest degree? That degree will be the degree of the entire polynomial. So this first polynomial, this is a 7th degree polynomial. This one right over here is a 2nd degree polynomial because it has a 2nd degree term, and that's the highest degree term. This right over here is a 3rd degree. You could even say 3rd degree binomial because its highest degree term has degree 3. If this said 5y to the 7th instead of 5y, well, then it would be a 7th degree binomial. This right over here is a 15th degree monomial. This is a 2nd degree trinomial. Now, the last thing I will, or a few more things I will introduce you to, is the idea of a leading term and a leading coefficient. So let me write this down. The notion of what it means to be leading. Well, it usually means, it can mean whatever is the first term, or the coefficient. If you're saying leading term, it's the first term. And if you're saying leading coefficient, it's the coefficient in the first term. But it's oftentimes associated with a polynomial being written in standard form. So standard form is where you write the terms in degree order, starting with the highest degree term. So for example, what I have up here, this is not in standard form because I do have the highest degree term first, but then I should go to the next highest, which is the x to the third. But here I wrote x squared next. So this is not standard. If I wanted to write it in standard form, it would be 10x to the 7th power, which is the highest degree term, has the degree 7. Then 15x to the third, so plus 15x to the third, which is the next highest degree. Then negative 9x squared is the next highest degree term. And then the lowest degree term here is plus 9 or plus 9x to 0. Now this is in standard form. I've written the terms in order of decreasing degree with the highest degree first. And here it's clear that your leading term is 10x to the 7th because it's the first one. And our leading coefficient here is the number 10. So there was a lot in that video, but hopefully the notion of a polynomial isn't seeming too intimidating at this point. And these are really useful words to be familiar with as you continue on your math journey. Plus 15.
Alright, as we have nerded out, the polynomial is just a bunch of terms in a math expression, right? And the coefficient is the real number before the unknown variable. Multiplying binomial. What is binomial? Alright. The bi probably means binomial, which is 2. And the nomial is the later part or the tail part of polynomial. Let's get into it and say what happened there.
So I have this big rectangle here that's divided into 4 smaller rectangles. And what I want to do is I want to express the area of this larger rectangle, and I want to do it 2 ways. The first way, I want to express it as the product of 2 binomials, and then I want to express it as a trinomial. So let's think about this a little bit. So one way to say, well, look, the height of this larger rectangle from here to here, we see that that distance is x. And then from here to here, it's 2. So the entire height right over here, is going to be x plus 2. So the height is x plus 2. And what's the width? Well, the width is, we go from there to there is x. And then from there to there is 3. So the entire width is x plus 3. X plus 3. So just like that, I've expressed the area of the entire rectangle, and it's as a product of 2 binomials. But now let's express it as a trinomial. Well, to do that, we can break down the larger area into the areas of each of these smaller rectangles. So what's the area of this purple rectangle right over here? Well, the purple rectangle, its height is x, and its width is x. So its area is x squared. Let me write that. That's x squared. What's the area of this yellow rectangle? Well, its height is x, same height as right over here. Its height is x, and its width is 3. So it's going to be x times 3, or 3x. It'll have an area of 3x. So that area is 3x. So if we're summing up the area of the entire thing, this would be plus 3x. So this expression right over here, that's the area of this purple region plus the area of this yellow region. And then we can move on to this green region. What's the area going to be here? Well, the height is 2 and the width is x. So multiplying height times width is going to be 2 times x. And we can just add that, plus 2 times x. And then finally, this little gray box here, its height is 2. We see that right over there. Its height is 2 and its width is 3. We see it right over there. So it has an area of 6. 2 times 3. So plus 6. And you might say, well, this isn't a trinomial. This has 4 terms right over here. But you might notice that we can add these middle 2 terms. 3x plus 2x. If I have 3 x's and I add 2 x's to that, I'm going to have 5 x's. So this entire thing simplifies to x squared plus 5x plus 6. So this and this are two ways of expressing the area, so they're going to be equal. And that makes sense, because if you multiplied out these binomials and simplified, you would get this trinomial. We could do that really fast. You multiply the x times the x. Actually, let me do it in the same colors. You multiply the x times the x, you get the x squared. You multiply this x times the 3, you get your 3x. You multiply the 2 times the x, you get your 2x. And then you multiply the 2 times the 3, and you get your 6. So what this, I guess you could say, this area model does for us is it hopefully makes a visual representation of why it makes sense to multiply binomials the way we do. And in other videos, we talk about it as applying the distribution property twice, but this gives you a more visual representation for why it actually makes sense.
Alright, why I love Kahan's demonstration about mathematical items? Well, it's simply because he always could be able to give us a visual graph for the math item. So you could say it's visually. So that would make the analogy more easy for us to understand. Let's have a look at this one.
We're asked to simplify or to expand 7x plus 10 to the second power. Now, the first thing I will show you is exactly what you should not do. Well, there's a huge temptation. A lot of people will look and say, oh, that's 7x squared plus 10 squared. This is wrong. And I'll write it in caps. This is wrong. What your brain is doing is thinking, oh, if I had 7x times 10 and I squared that, this would be 7x squared times 10 squared. We aren't multiplying here. We're adding 7x to 10. So you can't just square each of these terms. I just wanted to highlight this is completely wrong. And to see why it's wrong, you have to just remind yourself that 7x plus 10 squared, this is the exact same thing as 7x plus 10 times 7x plus 10. That's what it means to square something. You're multiplying it by itself, I guess, twice here. If you only did it once, you'd only have one 7x plus 10. So this is what it is. So we're really just multiplying a binomial or two binomials. They just happen to be the same one. And you could use FOIL. You could use the distributive method. But this is actually a special case when you're squaring a binomial. So let's just think about it as a special case first, and we can apply whatever we learn to this. So we could have just done it straight here, but I want to learn the general case so you can apply it to any problem that you might see. So if I have a plus b squared, we already realized that's not a squared plus b squared. That is a plus b times a plus b. And now we can use the distributive property. We can distribute this a plus b times this a. So we get a times a plus b, and then we could distribute the a plus b times this b, plus b times a plus b. And then we distribute this a, we get a squared plus ab, plus b times a is another ab, and I'm just swapping the order, so it's the same as this, plus b times b, which is b squared. These are the same, or these are like terms, so we can add them. One of something plus another of that something will give you two of that something, 2ab. We have a squared plus 2ab plus b squared. So the pattern here, if I have a plus b squared, it's equal to a squared plus 2 times the product of these numbers plus b squared. So over here I have 7x plus 10 squared. So this is going to be equal to 7x squared plus 2 times the product of 7x and 10, 2 times 7x times 10, plus 10 squared. So the difference between the right answer and the wrong answer is that you have this middle term here that you might have forgotten about if you did it this way. And this comes out when you're multiplying all of the different combinations of the terms here. And if we simplify this, if we simplify it, 7x squared, that's 7 squared times x squared. So 7 squared is 49 times x squared. When you multiply this part out, 2 times 7 times 10, That's 14 times 10, which is 140. And then we have our x, no other x there. And then plus 10 squared. So plus 100. And we are done.
Introduction to factoring.
You're probably familiar with the general term factor. So if I were to say, what are the factors of 12? You can say, well, what are the whole numbers that I can multiply by another whole number to get 12? So for examples, you could say things like, well, I could multiply 1 times 12 to get 12. So you could say that 1 is a factor of 12. You could even say that 12 is a factor of 12. You could say 2 times 6 is equal to 12. So you could say that 2 is a factor of 12, and that 6 is also a factor of 12. And of course, 3 times 4 is also 12. So both 3 and 4 are factors of 12. So if you said, well, what are the factors of 12? And you've seen this before, you'd say, well, you could say 1, 2, 3, 4, 6, and 12. Those are all factors of 12. And you could also phrase it the other way around. So let me just give an example. So if I were to pick on 3, I could say that 3 is a factor of 12. Or to phrase it slightly differently, I could say that 12 is divisible. 12 is divisible by 3. Now what I want to do in this video is extend this idea of being a factor or divisibility into the algebraic world. So for example, if I were to take 3xy, so this is a monomial with an integer coefficient. 3 is an integer right over here. And if I were to multiply it with another monomial with an integer coefficient, I don't know, let's say times negative 2x squared y to the third power, what is this going to be equal to? Well, this would be equal to, if we multiply the coefficients, 3 times negative 2 is going to be negative 6. X times x squared is x to the third power. And then y times y to the third is y to the fourth power. And so what we could say is, if we wanted to say factors of negative 6x to the third y to the fourth, we could say that 3xy is a factor of this, just as an example. So let me write that down. We could write that 3xy is a factor of negative 6x to the third power y to the fourth. Or we could phrase that the other way around. We could say that negative 6x to the third y to the fourth is divisible by 3xy. So hopefully you're seeing the parallels. If I'm taking these two monomials with integer coefficients and I multiply them and I get this other, in this case, this other monomial, I could say that either one of these, and there's actually other factors of this, but I could say either one of these is a factor of this monomial, or we could say that negative 6x to the third y to the 4 is divisible by one of its factors. And we could even extend this to binomials or polynomials.
Okay, when you look at this, if someone asks you, how can you determine if an item is a factor of a polynomial? Well, you answer it with, if this expression can be divided by an item, for example, 6 times x to the third power. If this item could be divided by this item, then we would say this one is an factor of the older expression.
Factoring quadratics by grouping.
Factoring quadratics by grouping. Yeah, let me get into it.
We're asked to factor 4y squared plus 4y minus 15. And whenever you have an expression like this, where you have a non-1 coefficient on the y squared, or on the second degree term, it could have been an x squared, the best way to do this is by grouping. And to factor by grouping, we need to look for two numbers whose product is equal to 4 times negative 15. So we're looking for two numbers whose product, let's call those a and b, is going to be equal to 4 times negative 15. 4 times negative 15, or negative 60. And the sum of those two numbers, a plus b, needs to be equal to this 4 right there. Needs to be equal to 4. So let's think about all the factors of negative 60 or 60, and we're looking for ones that are essentially 4 apart, because the numbers are going to be of different signs, because their product is negative. So when you take two numbers of different signs and you sum them, you kind of view it as the difference of their absolute values. If that confuses you, don't worry about it. But this tells you that the numbers, since they're going to be of different size, their absolute values are going to be roughly 4 apart. So we could try out things like 5 and 12. 5 and negative 12, because one has to be negative. If you add these two, you get negative 7. If you did negative 5 and 12, you'd get positive 7. They're just still too far apart. What if we tried 6 and negative 10? Then you get a negative 4 if you added these two. We want a positive 4, so let's do negative 6 and 10. Negative 6 plus 10 is positive 4. So those will be our two numbers, negative 6 and positive 10. Now, what we want to do is we want to break up this middle term here. The whole point of figuring out the negative 6 and the 10 is to break up the 4y into a negative 6y and a 10y. So let's do that. So this 4y can be rewritten as negative 6y plus 10y, right? Because if you add those, you get 4y. And on the other sides of it, you have your 4y squared, and then you have your minus 15. All I did is expand this into these two numbers as being the coefficients on the y. If you add these, you get the 4y again. Now, this is where the grouping comes in. You group the terms. So let's see. Let me do it in a different color. If I take these two guys, what can I factor out of those two guys? Well, there's a common factor. It looks like there's a common factor of 2y. So if we factor out 2y, we get 2y times 4y squared divided by 2y is 2y. And then negative 6y divided by 2y is negative 3. Negative 3. So that gets this group gets factored into 2y times 2y minus 3. Now, let's look at this other group right here. This was the whole point about breaking it up like this. And in other videos, I've explained why this works. Now here, the greatest common factor is a 5. So we can factor out a 5. So this is equal to plus 5 times 10y divided by 5 is 2y. Negative 15 divided by 5 is 3. And so we have 2y times 2y minus 3 plus 5 times 2y minus 3. So now you have two terms. And 2y minus 3 is a common factor to both. So let's factor out a 2y minus 3. So this is equal to 2y minus 3 times 2y times that 2y plus that 5. There's no magic happening here. All I did is undistribute the 2y minus 3. I factored it out of both of these guys and took it out of the parentheses. If I distributed it in, you'd get back to this expression. But we're done. We factored it. We factored it into two binomial expressions. 4y squared plus 4y minus 15 is 2y minus 3 times 2y plus 5. We're asked a expression. But we're done. We factored it.
You know what I often say? Those people are really like to transfer the form of an expression, for example, from this one into this form. But to be honest, I do not know why they want to do that, because that makes sense. I guess this form is already good enough. If you put it into let's say into the programming language, it could work. If you put it into the calculator, it would work. Why you have to transfer it into this form? That's not necessary, right? Factoring quadratics with perfect squares.
Factoring quadratics with perfect squares.
Quadratic expressions 4x squared plus 12x. Quadratic expression x squared plus 5x plus c is a...
We need to factor negative 4t squared minus 12t minus 9. And a good place to start is to say, well, are there any common factors for all of these terms? And when you look at them, well, these first two are divisible by 4. These last two are divisible by 3. But not all of them are divisible by any one number. Well, but you could factor out a negative 1. But even if you factor out a negative 1, so you say this is the same thing as negative 1 times positive 4t squared plus 12t plus 9. you still end up with a non-1 coefficient out here and on the second degree term, on the t squared term. So you might want to immediately start grouping this. And if you did factor it by grouping, it would work. You would get the right answer. But there is something you might be able to, or there is something about this equation that might pop out at you that might make it a little bit simpler to solve. And to understand that, let's take a little bit of a break here on the right-hand side and just think about what happens if you take a plus b times a plus b. If you just have, a binomial squared. Well, you have a times a, which is a squared. Then you have a times that b, which is plus ab. Then you have b times a, which is the same thing as ab. And then you have b times b, or you have b squared. And so if you add these middle two terms right here, you're left with a squared plus 2ab plus b squared. This is the square of a binomial. Now, does this right here, does 4t squared plus 12t plus 9 fit this pattern? Well, if 4t squared is a squared, so if this right here is a squared, if that is a squared right there, then what does a have to be? If this is a squared, then a would be equal to the square root of this. It would be 2t. And if this is b squared, let me do that in a different color. If this right here is b squared, if the 9 is b squared right there, then that means that b is equal to 3. It's equal to the positive square root of the 9. Now, this number right here, and actually it doesn't have to just be equal to 3. It might have been negative 3 as well. It could be plus or minus 3. But this number here, is it 2 times ab, right? That's the middle term that we care about. Is it 2 times ab? Well, if we multiply 2t times 3, we get 6t. And then we multiply that times 2, you get 12t. This right here, 12t, is equal to 2 times 2t times 3. It is 2 times ab. And if this was a negative 3, we would look to see if this was a negative 12. But this does work for a positive 3. So this does fit the pattern of a perfect square. This is a special type of, or you could view this as a square of a binomial. So if you wanted to factor this, the stuff on the inside, you still have that negative 1 out there, the 4t squared plus 12t plus 9, you could immediately say, well, that's going to be a plus b times a plus b, or 2t plus 3, 2t plus 3 times 2t plus 3, or you could just say it's 2t plus 3 squared. It fits this pattern. And of course, you can't forget about this negative 1 out here. You could have also solved it by grouping, but this might be a quicker thing to recognize. This is a number squared. That's another number squared. If you take each of those numbers that you're squaring, take their product and multiply by 2, you have that right there. So this is a perfect square.
So the mathematics is all about find patterns and applying rows into numbers. And along the way, you have to do some calculation or equality transferring, something like that. I think that's all about the math. No fancy inside of that. It's you can master it if you do enough or solving enough problems with right strategy and process. Okay, that's today's learning, and I'll see you guys in the next one. Bye.